Hello friends, welcome to TCPA, and we are going to solve this problem using slope deflection method. It's a continuous beam with a point load UDL, and I've deliberately assumed that the support C sinks down by 15 mm and the EI I have considered as 2000 kilonewton meter square. Okay, sign conventions would be clockwise as positive and anti-clockwise as negative. So let's get started with it. Step 1 is fixed end moments. So we have here one, two, three, and three bands or three segments, that is A, B, B, C, C, D, and this DE is a overhang. Okay, sort of cantilever, yeah, overhang. So the friction moment MFAB will be minus WB square A by L square. There is a fixed end moment for a point load acting at a distance of A. Though it is acting at center, but still I've used this particular formula, and it is minus 60 into 2 square into 2 by 4 square equal to minus 30 kilonewton meter, minus because at this end, that is AB, there will be a anti-clockwise moment, anti-clockwise fixed end moment, that is why minus. MFBA would be WA square B by L square, which is equal to plus 30 kilonewton meter, plus because it would be a clockwise. MFBC is minus WL square by 12, again anti-clockwise, so minus 40 into 4, that is L is 4, and divided by 12 equal to minus 160 by 3 kilonewton meter. MFCB is plus WL square by 12, and it is equal to 160 by 3, that is from here this friction moment MFCB. Then comes MFCD, which is again minus WB square A by L square, and here W is 30, so minus 30 into 1, this is B, this is A, and L is 3, so 1 square into 2 by 3 square equal to minus 20 by 3, and MFDC is WA square B by L square equal to 30 into 2 square into 1 by 3 square equal to 40 by 3 kilonewton meter, and MFDE is the cantilever moment, that is 15 into 0.6. So MFD is minus W into L equal to minus 15 into 0.6 equal to minus 9 kilonewton meter. Again, it's an anti-clockwise moment. This completes our step 1. Now step 2 is slope deflection equations. Okay, this is my beam that I have minimized here. So MAB is equal to MFAB plus 2EI by LAB into 2 theta A plus theta B minus 3 delta by LAB. So MFAB, which we found in previous step, was minus 30. 2EI by LAB is 4, that's 2 plus 2 4. Theta A is 0 because since this is a fixed end, there won't be any slope or there won't be any rotation at this point. Therefore theta A is 0. Here I have shown that why the theta A is 0. As you can see here, there is no rotation here, that is why it is 0. Theta B will be there because this is a roller support or a pin jointed support, that is why the rotation will be there, thus theta B is kept like that. And no deflection in segment AB because my C support C deflects and not support B. So for AB there is no deflection, hence delta is 0. When we simplify this, so MAB equal to minus 30 plus 2 EI by 4 into 0 plus theta B minus 0 obviously. So again simplifying it, we get minus 30 plus EI by 2 into theta B. Now MBA is MFBA plus 2 EI upon LAB into 2 theta B plus theta A minus 3 delta by LAB. Now if you don't know how these slope deflection equations are formed, then you can check my video in which I have derived these slope deflection equations, how they are formulated, and from that you will come to know how they are formed. Okay, so MFBA we found was plus 30, I guess, yeah, plus 30 plus 2 EI by 4 into 2 theta B, again theta A is 0 minus 3 delta is 0 by 4. Simplifying this, we get MBA equal to 30 plus EI into theta B. This is MBA. Now we'll write slope deflection equation for MBC. MBC is MFBC plus 2EI by LBC into 2 theta B plus theta C minus 3 delta by LBC. Now I hope you know how to write these. These are the first letter here, that is B, will be first rotation, C second rotation. So 2 theta B theta C. Again when I am writing for MCB, Here in the bracket it will be 2 theta c plus theta b, because it was CB. Now it is BC. Again here MFBC, and while writing for MCB I'll write MFCB. Okay, so whatever these two letters correspond, the same thing will be written in the equation as well. So MFBC was, I think, minus 160 by 3 plus 2EI by 4 into 2 theta B plus theta C. Now both of these joints will have rotations. Therefore theta B and theta C will remain, and now my support C also settles, and that is why delta will also be there. It settles by 15 mm, and we will write delta is equal to 0.015, that is in meters. 15 mm in meters will be 0.015. Now I have written the delta as it is. I have not written anything minus or plus. It is plus because the support, when my support C settles down, my BC gets rotated in a clockwise direction. See, when my support C settles down, my BC is rotated into a clockwise direction, and as we saw earlier that the sign conventions were clockwise is positive. So if my deflection is causing my beam to rotate in a clockwise manner, my delta or my deflection is positive. That is why I have substituted delta as plus 0.015 here. And then we simplify this equation, we get minus 160 by 3 EI by 2 into 2 theta B plus theta C minus 9 by 800. Okay, now we'll write equation for MCB, MFCB plus 2EI by LBC, that is length BC4, into theta C will come first now because CB, right? So 2 theta C plus theta B minus 3 delta by LBC. Again here delta will be positive only because my BC is getting rotated in a clockwise manner. So we substitute delta is 0.015, that is in meter. We get, after simplifying, as 160 by 3 plus EI by 2 into 2 theta C plus theta B minus 9 by 800. This is MCB. Now we'll write equation for MCD. MCD is MFCD plus 2E, and now I is changing. Okay, in the earlier segments, that is previous segments AB and BC, my I was same. Now I has changed to 2I, therefore I substitute here I as 2I. So 2AE into 2I by LCD, that is length of CD, into 2 theta C plus theta D minus 3 delta by LCD. Now uh, note carefully that delta will not be positive here. Why? Because there will be a anti-clockwise deflection. See, when my support C settles down, there is an anti-clockwise deflection here. My beam CD has been rotated in an anti-clockwise manner. Earlier this was the axis of my beam, and the CD has been rotated in the anti-clockwise manner. Therefore delta will be substituted as negative 0.015, because our convention is that anti-clockwise is negative. Therefore we are substituting delta as minus 0.015. Now simplifying this, we get minus 20 by 3 plus 4 EI by 3 into 2 theta C plus theta D plus 3 by 200. This is the slope deflection equation for MCD. Again writing for MDC, it is MFDC plus 2E into 2I by LCD into 2 theta D plus theta C minus 3 delta by LCD. Again delta will be negative only because it is anti-clockwise for this particular segment. Simplifying this, we get 40 by 3 plus 4 EI by 3 into 2 theta D plus theta C plus 3 by 200. Okay, and now the last is MDE. Okay, this MDE will be equal to MFDE only. Why? Because when my load acts at the point E, it tries to rotate my beam, or it tries to cause a clockwise movement. Okay, clockwise movement, right? 15 into 0.6 would be a clockwise movement. Now my support D has to offer an anti-clockwise moment of the same magnitude, which is MDE, right? Whatever these equations that we have written, that is MDC or MCD, are all the resistive moments that are occurring at all the joints. Okay, for example, MDC is the resistive moment occurring at this joint, and MD is also the resistive moment occurring at this joint, though we'll see later on that both of these have to be equal and opposite in natures. Okay, MCB that we have written previously would be the resistive moment at this particular support, and md is the resistive moment at this particular support, which is equal to this force into the distance, that is 15 into 0.6, which is equal to 9 kilonewton meter. And since it acts as anti-clockwise, the resistive would be anti-clockwise, therefore it is minus 9. So md will be equal to the fixed end moment itself. I've written all these equations here from MAB, BA, BC, CB, CD, DC and DE. Now the step 3 is joint equilibrium conditions. Now let us assume that all the previous these moments M, A, B, B, A, etc. are all clockwise in nature. Okay, that is a basic assumption that we are doing, that all these are clockwise in nature. See, what my tendency basically is that whenever I write moments, I write them into whenever I write resistive moments, I write them into blue color. Okay, that is the color code I have been following throughout my lectures. That is, all the resistive moments would be in blue color only, and all the forced moments will be in the red color. For example, these are the forces that are acting, all are in red colors, and whatever the resistive moments that would be produced due to these forces, they would be into blue color. So just for assumption, we'll assume that all the resistive moments at every joint, that is starting from MAB, MBA, MBC, MCB, MCD, MDC and MDE, all are clockwise in nature. Okay, now once we have shown all the resistive moments in blue colors, we have one question, that what are they resisting basically. Like this MAB, what is it resisting? It's a resistive moment, so of course it has to resist a force, because like for example, if I give a vertical force downwards and I want to resist it, I have to provide a vertical force upward, right? So the nature of the force has to be same for the resistive purpose. Okay, every force has an equal and opposite reaction, and the reaction and the force, the nature of both these things are similar. So if this is a resistive moment, it is resisting a force, a forced moment, that is MAB, and this forced moment is created due to this force acting on the span AB. Okay, you got it? I'll again explain. All these resistive moments that are formed here, MAB, BA, BC, CB, CD, DC and DE, all are resisting some forced moment, and all the forced moment are created due to the loading that is being applied on the continuous beam. So for AB, and due to this load, there will be a resistive moment of there will be a forced moment of MAB, to which this is a resistive moment. Again here on this side there will be a forced moment of MBA, to which this is the resistive moment. Again here MBC, CB, CD, DC and DE. Now if you see closely, then the nature of these force moment are exactly opposite to the resistive moments. So if these are clockwise, these are anti-clockwise. Clockwise, anti-clockwise, anti-clockwise, clockwise. Okay, so I hope you got the concept what I'm trying to explain, that if reactive moments are formed here, which we have assumed as clockwise, what are they reacting basically to? They are reacting to forced moments, and forced moments are caused due to these forces that are acting on our beams. So this is what you have to draw now in joint equilibrium conditions, and we have to now take every joint here. We have to simplify all these joints. So let us take joint B. At joint B, minus MBA minus MBC plus phi equal to 0. You got it how I written this equation, right? Minus MBA because it is an anti-clockwise forced moment, minus MBC because again it's an anti-clockwise forced moment, and plus phi because it is a clockwise forced moment. Okay, this is a force that is acting basically on the joint B, and it is equal to 0. I just simplified it here, MBA plus MBC equal to 5, and now I'll substitute the equations for MBA and MBC from the slope deflection equations. We get 30 plus EI theta B plus minus 160 by 3 plus EI by 2 into 2 theta B plus theta C minus 9 by 800 equal to 5. I've just substituted MBC and MBA, that's it. And now I have to simplify this whole thing. 2 theta B plus theta C by 2 minus 9 by 1600 equal to 85 by 3 EI I have taken EI on the right hand side, so it will go into the denominator, and again simplifying this, I get 2 theta b plus theta c by 2 equal to 19 by 960. I'll write this as equation 1. Now at joint C, what happens at joint C? Minus MCB minus MCD equal to 0. Okay, simple equation. Minus MCB minus MCD, because both are anticlockwise and there is no uh, forced moment acting again, like as in previous case, as in at joint B there was this 5 kilonewton meter force, but here there is nothing, so it is equal to 0. And again substituting these values or these equations, we get 160 by 3 plus EI by 2 into 2 theta c plus theta b minus 9 by 800 plus minus 20 by 3 plus 4 EI by 3 into 2 theta c plus theta d plus 3 by 200 equal to 0. Simplifying this again, uh, I get this equation into theta c, theta b and theta d, and E I have taken on the right hand side. Again simplifying this further, we get theta b by 2 plus 11 theta c by 3 plus 4 theta d by 3 equal to minus 181 by 4800. I'll write this as equation 2, equation number 2. Okay. Now at joint D, we have again minus MDC, right? Minus MDC minus MDE equal to 0. Substituting the equations for MDC and MDE respectively, we get MDC plus MD equal to 0, 40 by 3 plus 4EI by 3 into 2 theta d plus theta c plus 3 by 200 minus 9, because MD was minus 9, right, equal to 0. Again simplifying this, we get 8 theta d by 3 plus 4 theta c by 3 plus 1 by 50 equal to minus 13 by 3 EI. Simplifying further, we get theta d equal to minus 133 by 16,000 minus theta c by 2. Now what I've done here is that we have this particular equation in which we have only these two variables, theta d and theta c, and I have written theta d in terms of theta c so that I can substitute this theta d in my previous equations, that is in equation 2. Okay, and if I substitute this in equation 2, my theta d will be eliminated and I'll be left with only two variables. So let's see this further. I've given this equation as number 3. So theta b plus by 2 plus 11 theta c by 3 plus 4 theta d by 3 equal to minus 181 by 4800. This was our equation number 2. We substitute theta d, that is what we found in previous step, and we simplify this whole equation. We get theta b by 2 plus 3 theta c equal to minus 213 by 8000. Now we are left with only two variables, that is theta b and theta c. Let me give this equation as number 4. Again writing the equation number 1, that is 2 theta b plus theta c by 2 equal to 19 by 960. This is equation number 1. Okay, and we have these two equations and only two variables, so we can solve them simultaneously, right? And solving simultaneously, we get theta b as 1163 by 92,000 equal to 0.01264 radians, and theta c equal to minus 0.010982 radian. Okay, so we found these two rotations, theta b and theta c, and once we have found these two, theta c, we can easily find the theta d, because theta d is solely dependent on theta c. So substituting theta c into theta d, I get theta d equal to minus 2.8215 into 10 raised to minus 3 radians. Okay, so this is what we found. Now we just have to substitute these values into our slope deflection equations and we'll get uh, all the moments at particular joints. And here one thing that you have to notice is that positive means a clockwise rotation and negative is an anti-clockwise rotation, which is what our sign convention is. So MAB is minus 30 plus EI by 2 into theta B. EI again we substitute as 2000 kilonewton meter square, and theta B that we found previously we get minus 17.3587 kilonewton meter. Again we have to substitute in every slope deflection equation. MBA, this 55.2826, MBC is minus 50.2827, and the summation of these two should be 5 kilonewton meter, because at joint B there was a 5 kilonewton meter moment acting, right? Yeah. MCB is 32.7607, MCD is minus 32.7613. Now these two have to be equal. Okay, they are almost equal and they have to be opposite in nature. So if this is plus, this is minus. MDC is 9 and MD is minus 9. Again, these two have to be equal and opposite in nature. As per our sign conventions, if you follow them, minus is anticlockwise, plus is clockwise. So this is an anticlockwise resistive moment. This is a clockwise resistive moment, reactive moment. Anticlockwise, clockwise, anticlockwise, clockwise, anticlockwise. And I've just written all the moments here with their directions. That is anti-clockwise, which is minus 17.3587, clockwise here, anti-clockwise, clockwise, anti-clockwise, clockwise. Okay, and now we'll plot the bending moment diagram. Okay, so minus 17.3587, which was downwards, 55.2826 again downwards. How to plot these downwards values, because this particular reactive moment is going down, right? It will take my beam down like this, and again at this particular joint this moment is going to take my beam downwards. That is why we are plotting these two values down. Again, this moment, which is anti-clockwise in nature, will also, it is also going downwards, right? All these arrows you see, all these arrows are downwards. Okay, then 50.2826 again, it is downward somewhere here. 32.761 down, 9 down. If you want to be more clarified about how to draw this thing downwards, you can check the shear force and bending diagram lecture that I have posted in the channel. The link will be given in the show notes here, and we have to join them. This method is very simple. This is a shortcut method, and in detail I have discussed this method in that particular lecture. You can just watch that lecture if you want. Then it would be more easier. Since this particular lecture was about slope deflection and not about bending moment diagrams, I am not explaining it into detail. And now we have to superimpose the simply supported bending moment values. So if AB was a simply supported beam with a point load acting at center, the value would have been like this. The moment would have been like this, with this value as WAB by L equal to 60. Now this value is from this point to this point, but we require only this much value. Okay. Now how to get only this much value? We have to subtract from this value, that is this particular value. As you can see, this is a trapezoid here, and we have to find this ordinate, which is 36.3207. You can find it by linear interpolation, and we have to subtract this value from the whole value. So 60 minus 36.3207 equal to 23.6793. That is my actual bending moment value here. Again here, the simply supported bending moment diagram will be a parabola for a UDL with a value of WL square by 8 equal to 80. Again, we have to subtract this much value from this trapezoid. The value is 41.5218, and this value will be 80 minus 41.5218, which is equal to 38.4782. So 38.4782. The simply supported moment value for this will be again a triangle with a value of WAB by L equal to 20, and we have to again subtract this value, which is 16.9203, and subtracting 20 minus 16.9203 equal to 3.0797. This is the correct bending moment value, and we have to just join this to 0, because here the moment will be 0, right? This is the end of the beam and there is no support there, so it is 0. This is your final bending moment diagram here. Okay, and how this beam is going to get rotated will be like this. As you can see here, this C support C has synced down by 15 mm. It is not in line with all the other supports. It has synced down by 15 mm, and theta B here will be 0.01264 radians minus 0.01982 radians theta C, and this is minus 2.8215 into 10 raised to minus 3 radians theta D. Again, a point to note here is that theta B, since it is positive, it is a clockwise rotation, which can be seen here that it has rotated my beam here at support B into a clockwise rotation. Okay, if this was the original axis of the beam, then the beam has been rotated in a clockwise manner. Again, here theta C is negative, therefore it is anti-clockwise rotation. As you can see here, the beam has been rotated in an anti-clockwise manner. If this was the original axis, then the beam has rotated in an anti-clockwise manner. Similarly at D as well. This is the deflected profile of my beam. That's it. That's all for this sum. I hope you learned something valuable. Thank you so much. Please like, share, and subscribe, and click the bell notification icon. Thank you.